Okay. So today mostly we will be working upon the application parts of thermodynamics. It means that we have learned various process, right? So we haven't seen any fruitful use till yet, right? Like we have seen what are the various process efficiencies and other things, but we haven't applied all those process and to convert it into, like we haven't seen any useful work getting out. So what we would do today is that we'll work upon the applications parts, and first is that we'll work upon standard gas cycles. So let me hide it first. Yeah. No. So okay. So what we are going to work upon is gas standard cycles. So first thing is that we'll only see simply few cycles upon which various devices our which we see is working upon, right? So the first is that, like, when we are working on the cycle, then we have seen that the various process, like we have seen that the process can work completely in this gas phase. Then we have also seen that it can work in the wet regions also. Wet regions means what? That mixed phases also. So first thing we will be working upon on is gas power cycles. So what we are going to study is gas power cycles. So in the gas power cycles, the first one is Otto cycle. Otto cycle is also known as what? Spark ignition cycle. Okay. So see, let us see what happens into it. That not designing some work output, right? Like once we know various process, then our job is to find out that how can we get some fruitful work, right? So we started working upon various cycles. Then we tried to find out that how can we get some work. So the very first is Otto cycle, and this is the cycle upon which our petrol engines also work. So the petrol engine works upon which cycle? Otto cycle. So this is petrol engine. So now let us go to what this cycle constitutes. This cycle has four processes, namely what? Here you can look after that 1 to 2 will be compressing the gas isentropically. So can you see that here we will be having some amount of gas and then we are compressing it, right? Then we are compressing it, and then what happens that you will add some heat at constant volume. What does it mean? That once you have reached to 2, the momentarily there will be some spark and the heat will get added out and your piston will remain in that position. Here your piston is moving from 1 to 2, and here your piston is at that particular position, so V is constant. And then your gas is now, since it has got some heat, so it will try to expand its volume. Why? Because there is temperature increase. So now what happens that this gas is trying to push this piston in the downward side. So can you see that there is one downward movement of this piston? And now what happens is that the gas which was initially compressed at this point, the gas which was initially compressed at this point has now started getting expanded. So in that way it is pushing the piston to the outwards. And now then what happens is that you have reached to till this position. Can you see that your initial position is 1? So you have again reached to whom? From 4 to 1. 4 to 1, and that too in no time. what now what you have in here, you will be having now the burned air fuel mixture, right? So now you decide that this burned air fuel mixture is of no use to you. So what do you wish is that this should go outside. So what is that this is the heat rejection, means what your fluid is going outside, the working fluid has now gone outside. So again you are at what position, your initial position, and at this initial position there will be again some suction, means that there will be some fluid coming into it, and then you will compress it and the all. So what are the various processes associated with the Otto cycle is that isentropic compression from 1 to 2 you are isentropically compressing, 2 to 3 you are adding heat at constant volume, 3 to 4 isentropic expansion, and 4 to 1 your constant volume heat rejection. Okay, so this cycle is also called constant volume cycle. Constant volume cycle. So today we will not do problems, but we will see that how problems appears. So they would ask that in the Otto cycle, the heat is added at, what do you will say, that heat is added at constant volume. They might ask heat is rejected at what? Constant volume, and like that problems keeps on coming, right? Two things. So this is why this is all called constant volume cycle also. Okay, let us quickly move to the next. So here you can see what happens is that initially your volume was 1 and now you have got compressed to whom? V2. So your compression ratio R is nothing but V1 by V2. Can you see that initially you were at V1, means the volume was initially this one, and the after compression, means once you reach till this point your V2 is this one. So V1 upon V2, this will be always greater than 1, right? Why? Because V1 value is higher, V2 is short, right? And now from 2 to 3 you have added heat at constant volume, and 3 to 4 expansion, and 4 to 1 heat rejection. Okay, next. Now let us find out what is the efficiency of Otto cycle. So here we have drawn cycle on which axis? Here your cycle is drawn on what? This is pressure and this is volume axis. So on PV axis. So you should keep the diagram in your minds also. Why? Because sometimes they would ask you that which of the following shows Otto cycle. So what you need to find out is that at least there should be two constant volume and two isentropic process, then only you would identify that this is Otto cycle. Okay, and what is that? Heat addition and heat rejection is happening at constant volume. Why this is constant volume? Because constant volume is straight line only. Okay, now the same process is drawn on the TS axis. Then what I can see is that initially we have seen 1 to 2 was isentropic compression, means entropy is constant. So can you see from this point to this point, 1 to 2, the entropy has same value. So entropy, if this is S1, then entropy is constant. Similarly, then you are adding heat at constant volume, you reach to whom? 3. Then 3 to 4, what do you have is that isentropic expansion. So can you see that 3 and 4 are nothing but one line only? This is, can I write down at this point, this is S3 is equal to S4, here your S1 is equal to S2, right? And then you are rejecting heat at constant volume. Okay, so tell me from your experiences, like from thermodynamics, you have seen that dq upon t was ds. So tell me what is dq value, if I know the dq value is nothing but t into ds, right? And if you are working with whom? If you are working with ideal gas and constant volume, ideal gas and constant volume, then what is the heat addition and heat rejection? Nothing but change in internal energy. If you remember, this was nothing but change in internal energy. So can I write down now that change in internal energy means Q in where you have supplied heat from this region, then what is the Q in value? Can I write down this is U3 minus U2? Yes, I can. And this is nothing but CV into T3 minus T2. Similarly, where you are rejecting your heat, this point, this is what? Q out. This is nothing but U4 minus U1, right? Because this is the point where you are rejecting heat, and this is the point you are accepting heat. So this is CVT4 minus T1. Okay. So what is the efficiency? Efficiency, we know that this is nothing but your net work upon what? Heat input. And we have appreciated this fact that W net is what? Q net. So Q net, W net is Q net, and Q net is what? Q in minus Q out. Then if you solve this one, Q net upon Q out upon Q in, then this got converted into 1 minus Q out upon Q in, right? So 1 minus Q out upon Q in, you have just now seen that what is Q out and Q in. Can you see that you have seen Q out is 1 minus Q out is T4 minus T1. Q out is T4 minus T1, and what is Q in? CB T3 minus T2, T3 minus T2. Okay, so now your efficiency has somewhat came into picture, that this is nothing but the ratio of temperatures, and what is that? 1 minus T4 minus T1 upon T3 minus T2. This is equal to this one. Okay, so when we step more further from this point onwards, then what happens that we need to find out what are these ratio T1 upon T2 and T4 upon T1, T3 upon T2. Once we know these ratios, then we can move further. So can you see that process 1 to 2 and 3 to 4 are isentropic? For isentropic process, can I write down that T1 upon T2 is equal to V2 upon V1 to the power gamma minus 1? Where this comes from? We have seen this law, PB to the power gamma is equal to constant, right? Do you remember? And we are here, what is the assumption here is? Assumption here is that your working fluid is ideal gas. Okay, when your working fluid is ideal gas, then you can apply this law also, PB is equal to MRT. So using these two laws, we have reached this conclusion that T1 upon T2 is V2 upon V1 to the power gamma minus 1. One thing, so one ratio I somehow know, right? If anyhow, if I can know these ratios, then our job will be done. So let us try to find out what are these ratios. So T1 upon T2 is known, and this is equal to whom? This is equal to T4 upon T3 also. Why? Because the volumes at 1 and 2 are constant also. No, from 2 to 3 these volumes are constant. Now if you compare from PV axis, then 2 to 3 volume is constant and 1 to 4 volume is constant. So if I write down that, if I let us say that I am writing down T4 upon T3, okay, T4 upon T3, can I write down this is V3 upon V4 to the power gamma minus 1? And can you see that V3 is equal to V2 and V4 is equal to V1? So can you see that this ratio is nothing but equal to T4 upon T3? Yeah. So these two ratios now I know. Then if you come and put into this one, then what you can see is that your T1 upon T2 value is something. And if I see that T1 upon T2 is equal to T4 upon T3, then can I say that T4 upon T1, T4 upon T1 is equal to T3 upon T2? T3 upon T2. So can you see that this ratio would get cancelled out? Can you see that here? This is very important relation. This is very important relation. So can you see that this will help you to eliminate what? This one and this one. Then now you are left with whom? 1 minus T1 upon T2 only. And T1 upon T2 is nothing but V2 upon V1 to the power gamma minus 1. Okay. So I'm writing down here. Now can I write down neta is equal to 1 minus V2 upon V1, T1 upon T2 we have seen now. So this is V2 upon V1 to the power minus. So see that R V1 upon V2, if you remember, see here. I told that compression ratio, R is called compression ratio. Compression ratio, which is the ratio of what? Volume before compression divided by volume after compression. Okay. So can you see that volume before compression was V1 and volume after compression was V2. So this is nothing but R. So now if I see that V1 upon V2 is equal to R, so this value neta is equal to 1 minus 1 upon V1 upon V2 to the power gamma minus 1. Can I write? Yeah, obviously I can write. Why? Because V2 upon V1 is nothing but, see, V1 upon V2, this V2 will go on the what? Numerator. So this is again the same. So now I can write what is the efficiency of Otto cycle. So I'm erasing other rings and I am only using now the efficiency one. So can I write down efficiency of Otto cycle is equal to 1 minus 1 upon r to the power gamma minus 1, or in general you can remember like this one. This would help you to remember. Why? Because 1 to the power something is 1 only, right? So this is okay. So this is Otto cycle efficiency. So can we see that Otto cycle efficiency is varying with whom? Varying with the compression ratio. And second thing is what? The ratio of specific hits. Can you see? The gamma is nothing but the ratio of specific hits and R is compression ratio. So your Otto cycle efficiency is dependent upon what? The compression ratio and second thing ratio of specific hits. So I have shown you what is the variation of efficiency with the compression ratio. So if with the increase in the specific hits, can you see that your Otto cycle efficiency is increasing, and this is bound to happen. Let us see how. Eta is equal to 1 minus 1 upon r to the power gamma minus 1. If you increase this value, then what happens that this overall value is increased. And if this overall value is increased, this value, what happens with this value? This will also increase. And if this increases, this is 1 upon some increased value. So the overall value will get decreased. Then what happens is that your efficiency will increase. So can you see that with the increase in efficiency, with the increase in gamma value, your efficiency is increasing. Okay, this K denotes here gamma only. Okay, so with the increase in ratio of specific efficiency is increasing, and with the increase in compression ratio, this will also increase. Like let us say you are working with the same gamma, then can you see that if I increase this value again, if I increase this value, then this overall value will, what will happen, that this will decrease. Then if this decreases, then neta overall increases. Okay, so you would see is that, what you would see is that with the increase in compression ratio, let us say that I am working on this, like gamma is equal to 1.3. So with the increase in compression ratio, let us say when your compression ratio was 2, then for the same gamma, you were, your efficiency was this one. And now let us say you are working at 8. Then can you see that your efficiency has got increased? So what are the conclusions? Neta increases with the increase in increase in gamma as well as R. Okay. And one more thing, which is various time we have been asked in the exam, that what is the compression ratios for the gasoline engines? Gasoline engines means what? Petrol engines. Okay. So for petrol engines, this compression ratio, this varies somewhere around from 6 to 10. Can you see that that variation is somewhere around 6 to 10? So this is the variation. So sometimes they would ask you that what is the compression ratio range for petrol cycle or auto cycle, sorry, petrol engines or auto cycle. So what you would say is that this is somewhere around 6 to 10. Okay. So this is about auto cycle. So the questions will be nothing but like they might ask you what is the efficiency, how it changes, and then they can ask what are the various process, what is the range of efficiency, and if there is any combination, then you can think after that what they are willing to ask you. Okay. Now let us move to home. Diesel cycle. So this is the ideal cycle for what? Compression ignition engine. Compression ignition engine. Okay. So what is difference between gasoline engine and diesel engine? See, in your gasoline engine, means in petrol engine, there is a spark plug which sparks whom? Which sparks the air fuel mixture. So initially when I saw you here that there is some compression of gas, so here ideally you had, here ideally, if I say here ideally you had what? You had mixture of air and fuel. Here we had a mixture of air and fuel. This got compressed and then we provided some heat and then this got expanded and this got rejected. Okay. But in case of diesel engines, what happens is that your only gas will come into picture, like when only air will come into picture, and then again you will compress it. But what happens here is that your fuel will come, what you have another mechanism for fuel, and that fuel is compressed somewhere, and that fuel will come into picture. And I don't say that this is compressed, not compressed fuel. Why? Because compressed fuel we have here. Here what happens is that your fuel will come at this fuel injector and this will get sprayed. This will get sprayed into what? Into compressed air. Okay. And this compressed air will be having higher temperature, higher temperature. So what happens is that at this higher temperature, this fuel, when it comes into picture, this automatically starts burning. It automatically starts burning. Okay. So this is the basic difference between Otto cycle and diesel cycle. Here we have a spark plug. Here we have what? Fuel injector. Here your fuel air mixture was there. Here only air was compressed and fuel later got sprayed. Got the difference? And let us now move to that what are the differences in working cycles. So here also we have compression 1 to 2, which is isentropic, is like we had in what? In gasoline engine or Otto cycle. But in the Otto cycle, heat was added at constant volume, but here your heat is added at what? Constant pressure. So heat is added at pressure is equal to constant, and then again you have isentropic expansion, and then your heat is rejection. So heat rejection happens at, heat is rejected at, heat is rejected at constant volume. Yeah. So here what will be your heat input? Here, what will be your heat input? Because it is occurring at constant pressure. So here, instead of CV, what you will write? Your CP value will come into picture. Why? Because you are adding heat at constant pressure. Okay. So let us now work with whom? Work with efficiency. So there is two additional terms into this one. Let us understand what is that. There is, can you see that? Can you see that? Let me erase the inks first. Okay, let us see. There is one ratio initially in your Otto cycle. What was there, that V2 and V3 was like this one, right? But here we have V2 and V3 like this one. So let us find out what is this ratio. So this ratio V2 upon V3, or let us take the ratio of higher upon lower. So ratio V3 upon V2 is denoted by RC, is called, this is called cutoff ratio. What is this? Cutoff ratio. This is cutoff ratio. Okay. What is that? This ratio, volume upon this volume. And then we have all expansion ratio. So if I write down here, expansion ratio. So what is expansion ratio? This is the ratio of these volumes, V4 upon V3. So expansion ratio is V4 upon V3. Okay. So let us now move to whom? The efficiency part of diesel cycle. So this I have shown you what is compression ratio. So let us again work with whom? What is the efficiency? So efficiency part, we know that I'm solving here, that like derivation is not important, so that is why I have skipped, but let me show you quickly that efficiency, thermal efficiency is 1 minus what was the Q out upon what is the Q in, right? So Q in value is what? Q in value is the heat is added at constant pressure, and we have seen in our thermodynamics that when heat was added at constant pressure, it was equivalent to change in enthalpy, right? And what is that change in enthalpy here? H3 minus H2. So can I write down this is Cp T3 minus T2? Yeah. And heat out, what is this heat out value? This is U4 minus U1. Why I'm writing like this one, U4 minus U1? Because it is happening at what? Constant volume, and we have seen that heat interaction at constant volume was nothing but change in internal energy. So this value is CV T4 minus T1. So now if you put this ratio here, so your thermal efficiency now becomes what? 1 minus Cp T3 minus T2 divided by Cv T4 minus T1. Now this Cp upon Cv, this is nothing but gamma. Yeah. Oh, sorry. Cv value will be here now. See, Q out, this should be in the numerator now. So Cv T4 minus T1 divided by Cp T3 minus T2, and this is nothing but Q. Oh, this is efficiency now. 1 minus. So Cp upon Cv was gamma. So this becomes what? 1 minus 1 upon gamma multiplied by some factor. Okay. So let us look at here what it would come like. So this is 1 minus 1 upon gamma into Now let us take few parts common. So I am taking T1 from the numerator. So this is T4 upon T1 minus 1. And from denominator, if I take T2, so T2, this is nothing but T3 upon T2 minus 1. So now can I see that this is 1 minus 1 upon gamma into T1 upon T2, and let us see, these parts are not important. Like if I go on finding out these ratios and all, so I am just writing down you the derived one. So if this comes out as 1 minus 1 upon r to the power gamma minus 1 into rho to the power gamma minus 1 upon gamma times rho minus 1. So see, what I am trying to say is that this is the efficiency of diesel cycle. See, till this part we know now. So why I'm helping you to reach this one, that sometimes they would ask you in terms of ratio of temperature. So you should know that how we reach till this point. Now, how to remember the efficiency of her diesel cycle, because Otto cycle efficiency was simple. Otto cycle efficiency was simple. This was nothing but 1 minus 1 upon r to the power gamma minus 1. Okay, so this is the efficiency of diesel cycle. So let me erase this one and let us work with this one. Okay, so can you see few things, that this diesel cycle efficiency is nothing but 1 minus 1 upon r to the power gamma minus 1. This is nothing but Otto cycle efficiency, right? And now then you are multiplying some terms into this term. Okay, and what is that term? See how I am writing down that I have written RC minus 1 on the numerator, RC minus 1 in the denominator as well, and then I am taking gamma. So I am in the numerator, I am taking gamma. Why? Because numerator I am trying to make it more, so I am taking power, and here I am multiplying. Got the thing? So this is how this is remembered. Okay, you write down the efficiency of Otto cycle and then multiply it by whom? RC minus 1 upon RC minus 1. In the numerator I need to make it more. This is power gamma and denominator gamma min. Okay, okay. So this is the efficiency of diesel cycle. So can you see one thing? Can you see one thing? If your compression ratio is same, if R value is same, then can you see that this portion will help you to reduce, means this portion, what I have made, that this is greater than 1. Can you see that I have made it greater than 1? I have made numerator more than 1 by taking power here. So if this part is, means this value is higher, numerator is higher, denominator is lower. So can you say that this portion in the bracket is greater than 1? And if this is greater than 1, then what would happen is that this value will increase. Then for the same compression ratio, the diesel cycle efficiency will be less than Otto. Why? Because if I write down the Otto cycle, then I have 1 minus 1 upon r to the power k minus 1, if I write down in this language. Okay, and now in the diesel cycle what you are doing is that you are multiplying this with some higher value. So if you are multiplying this with some higher value, then this value got increased, and if this value gets increased, then this overall value will happen, what will get decreased. So that is why I am telling you that diesel cycle efficiency for the same compression ratio, for same R value, what will happen, that thermal efficiency of Otto cycle will be greater to whom, diesel cycle. So this is many time we have been seen that this has been asked to us. Okay, so please keep mind these things. Okay. Okay, then what is the range of compression ratio for diesel cycle? So for diesel cycle, it varies somewhere from 12 to 22, but for exam purpose, you can remember that this varies from 16 to 20 for diesel cycle R value, and for Otto cycle, you can remember that this varies from 6 to 10. What is I am telling you is that R value, and the variation of R is in this range. Okay, and if your RC value is 1, then this will, okay, let us not complicate that part. Okay, let us move further. There is one modification in this Otto and diesel cycle, and then we have reached to whom, dual cycle. So here what happens is that all the heat not in two processes. And what are those processes? The heat is provided in two process. One is through constant volume, and another is through whom? Through constant pressure. Okay, but what is important here, that two things, that heat is added at constant volume and constant pressure. Heat is added at constant volume only, and isentropic compression, isentropic expansion. So only thing you need to remember about dual cycle is that heat is added at constant volume and constant pressure, but first we do with respect to what, volume is equal to constant, and then we add heat, at pressure is equal to constant. Can you see, first we added at heat at volume is equal to constant, and then we added heat when our volume was constant. Okay, sorry, pressure was constant and then volume was constant. So this is about dual cycle. The efficiency formula is bit complicated, and most of the time you are not supposed to remember. You should just know that what are the process involved in this one, and this is it. Okay. And how do you relate your Otto cycle and diesel cycle? So if your RC value, like your compression ratio, this is what value? This is cutoff ratio, right? So if your cutoff ratio is equal to 1, if your RC is equal to 1, then what does it mean? That your V3 is equal to V2. Why? Because RC was the ratio of whom? V3 upon V2. And if this value is equal to 1, then V3 is equal to V2. And you can put it here also. If your RC value is equal to 1, then this will ideally get converted into what cycle? Into diesel one, sorry, Otto cycle. So that is why it is written here that RC, if RC value is 1, then this is got converted into diesel cycle, right? Okay. Now, so these three cycles were important for, like Otto cycle, diesel cycle, and dual cycles are important for IC engine parts. Now let us move to Brayton cycle parts, right? Means power cycles for gas turbines. So Brayton cycle, this is Brayton cycle. this is the ideal cycle for gas turbine. So most of the time, why I have written this as heading also is that most of the time we have seen sometimes questions appears like what is the ideal gas turbine cycle, or the ideal cycle for gas turbine, or they can ask that on which of the following cycles the gas turbine works. The answer is Brayton cycle. Okay, then what does this Brayton cycle constitutes is that we have one isentropic compression process in a compressor. Okay, and then we have constant pressure heat addition, and then we have isentropic expansion. Okay, and then we have constant pressure heat rejection. Constant pressure heat rejection. So can you see that this is somewhere relating to nothing but Otto cycle, but the way you have added heat is different. Yes. So in the this is how you can remember, like you should be able to recall things in the exam. So you can recall that your Otto cycle was, Otto cycle is constant volume cycle, V is equal to constant cycle. Okay, and your Brayton cycle, Brayton cycle, your Brayton cycle is pressure is equal to constant cycle. Okay, so we know these two things now. Okay, so depending upon, this is open cycle and closed cycle. Let me help you what is open and closed cycle gas turbine. So depending upon how you have added the heat, you have name it open cycle gas turbine and closed cycle gas turbine. So in open cycle gas turbine, what happens is that, can you see that your exhaust gases are not being recirculated? Your exhaust gases are going into atmosphere, going into atmosphere. Okay, but here here your exhaust gases are being recirculated, so that is why it has been named open cycle gas turbine, and this is closed cycle, closed cycle. One more important thing is that here can you see that we have combustion chamber. Here we have combustion chamber. So here what happens is that you are adding fuel to whom? Directly to the compressed part from here, like the gas is compressed and comes into combustion chamber, and then this is mixed and burned, and then it is expanded in the turbine and then left outside. But here what happens is that in the closed cycle gas turbine, here we have heat exchanger. Heat exchanger means what? That your here what happens is that you have burned the fuel somewhere else, like fuel, what fuel you were using, you have burned it somewhere else, and now you are exchanging the heat of that burned fuel with whom? With this compressed gas, and then this will get expanded into turbine. So can you see the basic difference between these two, open cycle gas turbine and closed cycle gas turbine, is that here you have combustion chamber and here we have heat exchanger. So one basic question is that what is the difference between these two? So they can ask you in an open cycle, or they can ask you that in a closed cycle gas turbine, combustion chamber is replaced with whom? Can we see that this has been replaced with whom? With the heat exchanger. So this is the basic difference between these two. So why this is? So that we are adding heat there. We are adding heat with the help of fuel directly, and here with the help of heat exchanger. So the basic difference is that here here your fuel part, is not getting recirculated, right? But if this air is to be recirculated, then you cannot add the fuel heat directly. Otherwise, what will happen, that in the compression chamber again, what you will have is that air plus fuel, but you don't desire to do that. So that is why we are burning fuel somewhere else, and we are working with the air only throughout the system. But here what do we have, that fuel is directly burned. So what is the advantage of this one is that you can burn the cheaper fuel also. Why? Why? Because the fuel part is not coming into the cycle, but here you don't have that freedom because your fuel is going into the cycle. So you will have to keep mind that your turbine is consisting of what? Turbine is consisting of a rotor on which number of blades are attached, and if you are not using the quality full fuel, then what would happen is that they might erode these turbine blades, and these are very expensive. So that is why we cannot afford cheaper fuel here. Can't afford cheaper fuel. Okay. So let us now understand the cycle once we understood the difference. See, what would happen is that here you have the fresh air, and now it has got compressed. So its pressure as well as temperature has got increased, and then you increased its heat, what, temperature only by adding some heat. So from here to here, what would happen is that your pressure is constant. This in this chamber pressure is constant, but your temperature has got increased. Then you came into what? Turbine. So here what happens is that your fluid has got expanded, so its temperature got decreased and pressure also got decreased. And what about volume? Volume has also got decreased. Okay, so all temperature, pressure and volume got decreased, and what remained constant? Entropy remained constant. And then you came into heat exchanger. Here you are rejecting heat to whom? To atmosphere. Okay, to atmosphere you are rejecting heat, so that you could reach to which condition? Inlet condition. What was inlet condition? T1. So you could reach to T1. So here what happens again? Your pressure is constant, only decrease is what? That your temperature got decreased. So let us now see the PB and TS cycles of a Brayton cycle. So let me help you understand. So in this is your TS cycle and this is PB. Then can you see that I told you 1 to 2 it was isentropic compression, and then constant pressure heat addition, and then isentropic expansion. So this is expansion, where expansion in turbine, here heat addition, sorry, compression in what? In compressor. Okay, and then you have heat addition through what? Heat exchanger. Yeah, and then you have the heat rejection again in the heat exchanger. So now I hope that you can visualize the process, that this is the compressor part, then you got into heat exchanger, then you got into turbine, and then you came back to again compressor. So here your, can you see that your temperature got increased? Here again the temperature got increased, and here temperature got decreased, and again temperature got decreased. Let us now go to whom? The PV cycle. So can you see that 1 to 2 your pressure is increased? Can you see that your pressure has increased from 1 to 2? I told you that in compression pressure is increased. And what about volume? So volume, can you see that initially you were here and now you are here? So volume got decreased, volume decreased, and pressure got increased in what? In compressor. So how we can draw this PV cycle in compressor, we know that from point 1 the pressure will increase and volume will decrease. I know. Then 2 to 3 we have seen that this is constant pressure heat addition, and then 3 to 4 this is isentropic expansion. Then what happened is that I told you in the expansion part pressure got decreased. Can you see that the pressure has decreased from 3 to 4? And then I told you that the volume will increase in the expansion part. In the expansion part I have told you that volume will increase. So what would happen is that volume will increase from V3 to V4 and entropy has remained constant. Okay, and then from 4 to 1, then from 4 to 1 what happens is that your temperature, your 4 to 1 your temperature got decreased, and moreover what happened, it happened at constant pressure. Pressure is equal to constant, and volume has also what, decreased. Definitely, like if you work with PV is equal to MRT, and if pressure is constant, temperature decreases, then what happens is that in order to balance it, the volume also has to decrease. So that is why it has decreased. Okay. Now, again for efficiency part, what you would do is that you will try to find out what is Q in and what is Q out. So what is Q in? Q in is this part, right? And can I write down Q in is this part, this part? So this is nothing but happening at constant pressure. So change in enthalpy. So can I write down Cp T3 minus T2, and rejection part again at constant pressure. So this is again change in enthalpy Cp T4 minus T1. Then when I go to find out what is the efficiency, so then again I write down 1 minus Q out upon Q in, 1 minus, I write this one, and then you have reached to this one. So here can you see that neta thermal, again you can prove that T, you can remember this part, that T1 T3 is equal to T2 T4, or you can see that T4 upon T1, this we have proved once, so we can prove it again. T4 upon T1 is T3 upon T2, so this part will get cancelled out, so only thing will be remaining is T1 upon T2. So let us now see how we can write down the efficiency of Brayton cycle. So neta thermal of Brayton will get reduced to what, 1 minus T1 upon T2. So can you see that here we can write T2 upon T1 is equal to P2 upon P1 to the power gamma minus 1 upon gamma. So this P2 upon P1 here is called compression ratio. Earlier we have seen in case of Otto cycle, compression ratio was the ratio of volumes, but here your compression ratio is the ratio of what, pressures. So then when you go to write down this one, then can you see that this is nothing but 1 minus 1 upon R. Why? Because P2 upon T2 upon T1 is P2 upon P1. So can I write down this one as P1 upon P2 to the power gamma minus 1 upon gamma? And I told you that this value is R. So now if you go to write down the efficiency, then what you would do is that I'm writing down the final expression here. Thermal efficiency is 1 minus 1 upon R to the power gamma minus 1 upon gamma. So this is how we should remember the efficiency of Brayton cycle also. Again now, can you see that efficiency of Brayton cycle is part of what? Compression ratio and what? The index of compression, that is gamma, or the ratio of specific heats. Okay. So can you see that the pressure ratio here and Brayton cycle efficiency here? So can you see that with the increase in pressure ratio, you can see that the change in what? Efficiency. And what is the typical pressure ratio for gas turbine. This question can appear sometime in the exam. So we can remember that this varies somewhere from P5 to 20. What is this called? RP. RP means pressure ratio. So you should know that the here the compression ratio was ratio of pressures. Okay. Or in order to avoid confusion, what do we name it is? It is pressure ratio. So in order to avoid confusion, we call it pressure ratio. Okay. Now, okay. Now I have tried to show you something that this is Tmax, Tmin and all. So then you can think that if with the increase in compression ratio, I can increase the Brayton cycle efficiency. But what happens is that here you have one part which is called compressor, which is a work consuming device. Here we have compressor, right? And this compressor is work consuming device. Yes or no? Yes. So if this compressor is work consuming device, then if I keep on increasing the pressure ratio, then definitely I would, if I increase the pressure ratio, then my thermal efficiency will increase. There is no doubt over that. But what happens with the increase in pressure ratio? Your compressor input part has got also increased. So let us say that this is drawn for T max is 1000 Kelvin and T minimum is 300 Kelvin. So can you see that with the increase in compression ratio, your compressor work will also increase, and if your compressor work got increased, then your W net value, which is equal to what your turbine has got and what your compressor has got consumed. So can you see that this net work is the difference between turbine work and compressor work, and if you this compressor work got increased, then my W net value will always decrease. Yes. So if my W net value is decreased, then what is the benefit or of having higher efficiency if I am not able to get the required amount of what network? So this is how it got represented on a cycle. So let me help you to understand. See, initially if your pressure ratio was this 2, then your efficiency was lower, but you were getting some what work output. Then if you have increased this pressure ratio, then you have got to whom pressure ratio somewhere, let us say 8.2. So here you can see that you have got net W net. But here can you see that in this diagram, like when your RP value is 15, your W net value is very less. Why? Because we have seen that what is W net, the net area of this curve. So can you see that the net area of this curve is few compared to these two? So that is why when you have increased your compression, this pressure ratio, then what happens is that your net work is always decreased. Okay. I hope you understand. Yeah. Then there is one important term called, what is that? Back work ratio. Very important. Back work ratio. So back work ratio, it is the ratio of compressor work, means what your compressor has consumed, compressor work, compressor work divided by whom? Divided by turbine work. So this is called back work ratio. What is, how do we denote it as? RB. And back work ratio, it is the ratio of compressor work upon turbine work. Okay. And then we have work ratio. Then we have work ratio. Work ratio is nothing but 1 minus RB. That is, can I write down that this is net work ratio 1 minus RB is what? Turbine minus compressor, and turbine minus compressor is nothing but net work. So work ratio, can I write down this is nothing but net work divided by turbine work. This is very important. Sometimes what they would do is that they will give you the hints for turbine work and compressor work, and they will be asking you that tell me what is the back work ratio, what is the work ratio, and like that. Okay. So can you see that your back work ratio will be less when you are working with higher temperatures, uh, with higher pressure ratio? Why? Because your compressor work will be increasing, right? So if your compressor work gets increased, then this value will get decreased. Yes or no? Why? Because here you will be dividing with some constant value. So let us say that if your compressor work has got increased, then what happens is that, see, let us say that once when I was working, then initially I was consuming 10 kilowatt and my turbine work was 20 kilowatt. Now my turbine work has increased to 15 kilowatt, but my value of this turbine work was 20 only. So can I see that here my RB value is 10 by 2 is 0.5 only? And what about this one? This is RB is equal to 15 upon 20. So this is 0.75. So work ratio means back work ratio will be higher when you are working with higher pressure ratios, but your work ratio is decreased. Work ratio will be decreased. I was interested in whom that what is my work ratio. Work ratio directly tells you that what is your net work and what is your turbine work. So the ratio of these two. So when your back work ratio is increasing, then your work ratio will automatically got decreased. So when you are working with higher pressure ratios, for higher pressure ratios, what happens is that this is called RW work ratio. This gets decreased. Okay. Now there are some modifications in the Brayton cycle in order to try to find out that if we can improve this efficiency of this Brayton cycle. Okay. Okay. So before that, one question might be arising in your mind that if this is so, sir, if this is so that with the increase in RP I am getting uh, network less, then is there any pressure ratio? If I will be working about that, then I will be having my W net max. So yes, we have. And what is that called? That RP optimum. What is that called? RP optimum. RP optimum. RP optimum is when your this ratio is T maximum divided by T minimum, to the power gamma upon 2 times gamma minus 1. Can you keep this in mind? This RP optimum value is, optimum means what? If you are working on this one, then you will be having your net W net max value as the what? Maximum one, right? And then we have what is the RP max we can work upon? RP max value. See the difference between optimum and max. This is nothing but T max upon T minimum to the power gamma upon gamma minus 1. So can you see that RP optimum, RP max, RP max is nothing but RP optimum's whole square? Can you see? Okay. Yeah. And what is that temperature? Like when you are working with the RP optimum, then what is this value? Like we know T max value and T mean value will be fixed in a cycle. Yes. Then there are temperatures here. Can you see that if I am fixing this value is temperature max value? Yes or no? Yes. And this is your minimum value. Then is there any relation that T2 and T4 should be something? For maximum work output, for max work output, for max work output, T2 should be equal to T4, means I am telling you that these two temperatures should be equal, and should be equal to what? Square root of T1 and T3 means T maximum and T lower. So can I write down that T2 is equal to T4? It is nothing but square root of product of T max into T minimum. Okay. Then what is W net max value? W net max value is equal to nothing but Cp is anyway will be multiplied into root over T max minus square root of T mean whole square. So we should mind these words now. Now let us move to what that is there any modification in a Brayton cycle possible so that I can get higher efficiency? And I would say yes, there is. See, what happens is that you are trying to add heat to the home, the gas which comes out of the compressor. Yes. So what I would do now is that we are rejecting heat somewhere from 1 3 to 4. If you see that we were initially rejecting this heat, like we were rejecting this heat, right? After expansion we were rejecting this heat, and then what happens is that we are adding heat to the to whom the one which comes after out of the compressor. Then my idea is why I cannot do one thing like that, that if I do one thing, that if I will apply a regenerator, what it would do is that it will absorb heat from whom, it will absorb heat from whom, the gas which is coming out of turbine, and then it would apply or provide that heat to whom, the gas which is coming out of the compressor. So what regenerator does is that absorbs heat coming from the turbine, and what does it do, and provides heat to whom, and provide heats to whom, the gas coming out of compressor. So in this way what you are trying to do is that your heat in value is what, decrease. You are trying to decrease your heat input value. So this is very important, that you are trying to save some heat input value, and what is your efficiency is 1 minus q out upon q in. If you decrease this value, then what happens is that if you decrease this value, this overall gets what? No, let us not understand in this way. Like we should simply understand that if we are able to decrease the amount of heat supplied, if we are able to decrease the amount of heat supply, then what would happen is that my efficiency will be having chances of what getting improved. My efficiency will have the chances that it can get improved. So this is the one of the modification which is possible, which can increase my efficiency. Okay. But this, there is one condition when you can apply this one, is that it is effective at what? Your low pressure ratios. Why I'm telling you is this, that if your pressure ratios is higher, then what happens is that your compressor output will be also higher. But in any case, that if your compressor output temperature is higher and this exit temperature is lower, then you cannot apply heat from this one to this one. Why? Because this is at low temperature and this is at higher temperature. So what will happen, that there will be reverse heat transfer, so which you do not desire. So that is why this will be effective at low pressure ratio, very important. And and for low ratios of whom, minimum temperature, minimum T minimum to T maximum. Yeah, I know this fact, that whenever your T minimum is low, then only you can compress it, and your temperature T2 will be what? Like when you are compressing from 1 to 2, if this value is less, then T2 is also less, and if this value is less, then only you can add some heat from this to this. Otherwise, there is no possibility. Okay, so one more important fact, that what is efficiency of a regeneration cycle. So this is equal to 1 minus T1 upon T3. What is T1 T3 we have seen in the cycle, right? And into rp to the power gamma minus 1 upon gamma. So sometimes they can ask you this formula even, so we should keep in mind what is the thermal efficiency of a regeneration cycle. Regeneration cycle is this one. Here we are multiplying with the ratio whom? T1 upon T3. So please keep in mind. Okay. And what happens here is that your thermal efficiency gets increased. Okay. For same W net, for same W net. Why? Because there is no effect, there is no effect in what? In compressor work. And there is no effect in compressor work 1 and in turbine work. These two are unchanged, but only change is what? Heat supply has got decreased. Heat supply has got decreased. Then if I compare the thermal efficiency, then thermal efficiency is nothing W net upon Q supplied. If this Q supplied gets decreased, then what happens is that this thermal efficiency will increase, but provided what? That you are getting same W net. Okay, clear to everyone? Yeah. Okay, next. Now See, there is one modification called intercooling, and there is one more modification called reheating, and then there is one more modification called regeneration. So regeneration we have seen, right? So let us now see what is intercooling and reheating. So I have included a couple diagram, so I can teach you all things simultaneously, but you can understand it separately also. So let me show you how. See, let us first go to whom intercooling. So intercooling is what? Let us understand what is intercooling. In intercooling, what happens? Number one is that you are not compressing, or let us say that you are willing to compress from P1 to P2. So what you will do is that you will not compress that one in one go, but what you would do is that you will compress it to some intermediate temperature, let us say Pi, and then you will cool this one. You will cool this one, and then you will again compress this Pi to whom? P2. Got the idea? Why we are doing this one is that we are trying to convert this process into isothermal one, isothermal, so that we can save some work, so that we can save save some compressor work. Got it? If you are intercooling, then let me help you understand it with the respect of PV diagram. So let us say that you were at point 1 and you are trying to compress it to P2. Okay. So this is without intercooling. Okay. And this is your pressure axis, this is your volume axis. Now what happens is that you are not cooling, you are not compressing it in one go, but what you are doing is that you have compressed till some intermediate value, and then you have cooled it, and then you have again compressed it. So what happens, can you see that initially, oh no, see, just one thing. No, see, what happens in intercooling? Let me help you understand in better manner. So what happens in intercooling? Let us say that this is your work 1 to 2. This is your compression on PV axis. This is 1 to 2. Okay. Now what you have done is that you have compressed it to some lower pressure, and then like you have compressed it to some lower pressure, and then you have cooled it, and then you have reached to another pressure. So can you see that you have followed this path, you have started following this path? So you initially saved how much work? This area. Why? Because your initial work, if I if this was my initial curve, then what is the initial area? Like what is the initial area you are consuming? This one. Okay. This is your pressure axis and this is your volume axis. For open system, work done in open system is negative VDP. Okay. Open system work is negative VDP. So that is why we are trying to look after on the which axis? Pressure axis again. Now if you are trying to intercool it, then what you would do is that you have compressed till this point, and then you have slightly deviated, and then you have compressed it again to P2. So can you see your new area is what? Your new area is this one. This is only the work you have consumed, right? So this is the amount, which you are able to save through intercooling. So in the intercooling, what happens now? I hope the idea is clear. Okay, now let us go to whom? Now let us go to whom? To the reheating. See, what happens is, let us, you are working in turbine cycle, then what you are doing is that you have compressed, and then you have added heat, and then you have expanded it into the turbine. So what happens is that when you are already here, then what is the idea? That can't you heat it again to this temperature again? Like if you are in this temperature T3, this is 1, this is 2, this is T3. Then if you have expanded till this point, then my idea is to, why don't you expand it, heat it again at what? Constant pressure, and then you expand it again in the another turbine, right? So one turbine is here, another turbine is here, and then you cool it back into the what? Heat exchanger. So this is what the idea of what? Reheat. So what happens in the reheat? You will get W net increased. W net increase. Why? Because your compressor work is same, but your turbine work has somehow got increased. So your W net gets increased for same mass flow rate. Can you see that mass flow rate was same for same mass flow rate? So can you see what is the benefit of reheating? Is that for the same mass flow rate, what you have achieved is, for the same mass flow rate, what you have achieved is that you have more W net. But what about efficiency? What about efficiency? We cannot say what happens to this one. Why? Because this will depend upon the amount of reheat you have supplied. Why? Because W neta is nothing but W net upon Q supplied. Yeah, but what you have done here is that your Q supplied has got increased. Why? Because you have supplied it once here and here again while reheating. Okay, so your W net obviously has got increased, but this has also got simultaneously increased. So the relative magnitudes would decide that what happens with the efficiency. Got the idea? And regeneration, we have seen efficiency increases. And what about intercooling? So in intercooling, again, in intercooling, if I draw the diagram for TS diagram for intercooling, then how it would look like is, see, you have compressed it to someone, and then you have decreased it, you have cooled it, and then again you have compressed it, and then you have provided heat, you have expanded it, and then you. So this is the portion you have done intercooling. And intercooling done at pressure is equal to constant, and you have tried to reach to whom, like let us say that this was T1, and then if this was T2, then you have tried to reduce back to whom? T1 again. So can you see that initially you were supplying heat? If this was no, let us say that if there was no intercooling, then your heat supply was from T2 itself. But now can you see that your heat supply is from somewhere here? Okay, so now your heat supplied, again, what is that magnitude? What is the magnitude of heat supply would tell you that what is the change in what? Efficiency. So again, we can say that, yeah, there is increase in W net, like your W net has got increased, but what happens with the Q supplied will decide the change in efficiency. So that is why the intercooler part, the reheater part, and the regenerator parts are coupled together, and then the cycle is working on all of these together. Okay. So let me help you. One thing is that whenever you are writing W of turbine, then what you would do is that what is the expansion in turbine? Okay. So here what happens that there is turbine 1 work and work done is turbine 2. So here what you will write down, the work done in turbine 1, work done in turbine 2. What is work of compressor? So what is the work of compressor? Compressor 1 plus compressor 2. What is Q supplied? Q supplied is combustion chamber, like what you have provided, combustion chamber, Q combustion chamber, and plus what? Q in reheater. So don't forget to look after these magnitudes. Okay. Now, there is one ideal condition for perfect intercooling and perfect reheat. So, perfect intercooling, I am writing this with the respect of this one. Then you are desired to reach from P1 to P4. Then what your question is that what is this P2 and P3? And P2 is equal to P3 here. Okay. Why I have told you that the intercooling is happening at constant pressure. So whatever pressure you have here, the same pressure is here. So what is the intermediate pressure? So intermediate pressure is nothing but the square root of P1 and P2, means that the limits. Got the idea? Let us say that if the initial pressure was 10 megapascal and the final pressure is 30 megapascal, then they would tell you that in the first compression, like from P1 you are compressing till Pi. So what is the magnitude of this Pi? This is square root of P1 and P2 for perfect intercooling. And then they would ask you that what is the intermediate temperature? Then what is the intermediate temperature? So till what point you would cool? So see, initially you had temperature T1. So what you would do is that you have T3 here. So T3 will be equal to T1. Please mind, I am writing with respect to this diagram only. So what I am trying to say you is that when you are at P2, then from P2 to P3 your pressure is constant. But I told you that what? That your temperature was decreasing, right? So temperature, then question is that till what point I should cool? So I should cool to whom? T3, I should cool to what? T1. Okay, got the idea? Next is perfect reheat. When we will be having reheat, for perfect reheat, what happens is that uh, you would see here you have combustion chamber. From combustion chamber you have T6, and then after reheat you have temperature T8. So for perfect reheat, T6 value is equal to T8, and work done is turbine 1 is equal to work done in turbine 2. Okay. You should mind these words. See, I'm helping you to know those things only which you should know. Okay. Okay, so this summarizes about what? All about your gas power cycles. So gas power cycles is done. Now let us move to home. Let us move to vapor power cycles. Vapor power cycles. So we have Carnot vapor cycle. So this cycle which I have drawn here is Carnot vapor cycle. Carnot vapor cycle. So what happens in the Carnot cycle? Can you recall from the Carnot cycle? Can you recall that we have two isentropic process and two isothermal process, heat addition and heat rejection. So now let me tell you that what happens in this cycle, that from 1 to 2 is the boiler part where you have isothermal heat addition. We have isothermal heat addition. Okay, and then from 2 to 3, what do we have is that isentropic expansion. Okay, and then from 3 to 4 we have isothermal heat rejection. Isothermal rejection. Okay, and then 4 to 1 we have what is that? Isentropic compression. And this part is called boiler part, or economizer, we can sometimes tell. This is which part? No, this is boiler only, not economizer. This is turbine part. This is condenser part. And this is the pump part, means through which you are pumping the fluid. So can we find out the efficiency of this Brayton cycle? So here your working fluid is what? Water. Working fluid is water. So can you see that water has started its travel from somewhere, and then it has reached to what? Let me help you know. Let me clean this part. So can you see here that here we are working in which region? Wet region. This is wet region, right? So it is difficult to work in wet regions for whom? For pumps, like pumps. Okay, and there is one more thing, is that when you are in this region in 2 to 3, then you are working with whom? Turbine. And can you see that here you have wet region? Wet region means what? At 3, at 3, x value means dryness fraction. Dryness fraction we know, right? So dryness fraction is less than 1. If dryness fraction is less than 1, then what does it mean? That there will be some amount of moisture also, and then this moisture can hamper your turbine blades. So that is why we do not work upon Carnot cycle. Why? Because there is lot of difficulty associated with the Carnot cycle, Carnot vapor cycles. And what is that? That you have limited device control which can work in which region. Like you will be not able to find out those pumps which can work in wet regions. Why? Because here you are pumping this fluid from this point to this point, from point 4 to point 1 you are trying to pump the fluid. So here you will have to install what kind of pump which can handle the fluids of which region? Wet region. Like here you have moisture also, and here you have fluid also. So this is not possible. Okay, and this is the major difficulty, this part and this part. Okay, so that is why we are not working with the Carnot cycle. Got the idea? Okay, so then if you are not working on that cycle, then sir, tell me what is the cycle which is ideal for vapor power cycle? So that is Rankine cycle. So Rankine cycle, yeah. So your process has started from this point. Like here you have added fluid, what? Some heat to the fluid, and then you have expanded this fluid into the turbine, and then you rejected this fluid's heat. And then what you have done is that you have increased its pressure with the help of pump. Got the idea? Here you have started working and then you have added some heat QH, and then you have some work output, and then you have rejected Q net, Q outside, and then you here what you have done is that work input. Why? Because you are trying to hear your pressure, like if you remember, can you remember that these are constant pressure lines? Then can you recall that these pressures are not same? Like this pressure, if I say P2, this I say this is P4, then can you see that P2 is greater than P4? Then in order to reach from this point to this point, what you would do is that you will have to increase its pressure, and pump are those devices which can increase the fluid's pressure. But why we are not working with the Carnot cycle? The reason is that we are difficult to find, it is difficult for us to find those pumps who can handle the fluids of what? Mixtures of what? Liquid and vapor. So that is why we are avoiding. And moreover, here what do we have is that in wet regions, here we have moisture, and our turbine blades are made with what? High, in high cost what? Alloys. So those alloys can get deteriorated, that might get rusted. So that is why, in order to get relief from those ones, we are not working on the Carnot vapor cycles. So what is we are working upon is the Rankine vapor cycle. This is nothing but just the enhancement. This is nothing but just the enhancement of your what? Carnot cycle. So see what we have done in Carnot cycle. See, initially your Carnot cycle was this one only. If you can recall, then your Carnot cycle was this one only, right? So what I have done here is that I have increased the Carnot cycle limits. So what I have done here is that I have gone into superheated region. Which region? Superheated region. Then what is the benefit of entering into superheated region? Then now if you have expanded this one, then can you see that as soon as it has entered into the wet region, your expansion is done. This is your expansion, right? So now you are very close to whom? Very close to, you are very close to whom? Very close to what? X is equal to 1, or I can say that this is dry and saturated state. Dry saturated state, this is right. So I am close to that region again. And then what you have done in the when you were trying to reject the heat, you have gone till saturation curve. Can you remember that saturation curve? At the saturation curve, only fluid part was existing. So here what happens is that you are at saturation point. Now the difficulty which Carnot cycle was posing to you, those difficulties are countered with whom? With the help of Rankine cycle. So this is nothing but just the extension of whom? Just the extension of Carnot cycle. So what happens here is that you have some pump, you pumped this fluid to whom? Boiler. You pump this fluid to whom? Boiler. So here your boiler has got started, you poured some heat into it, and then you have expanded it into the turbine, and then your condenser rejected the heat, and then this is supplied to the pump, and then your pump fluid pumps this fluid to the boiler pressure, and this is how this is working. Okay, so what are the various process into this one? First one is isentropic compression in pump. So can you see that there also we were doing nothing but isentropic compression? So this is just the extension of that one. But here, instead of constant temperature heat addition, what we are doing is that we are working on constant pressure heat addition in boiler. So this is one difference. Why? Because if this was Carnot cycle, then your heat addition part started here, right? But in case of Rankine cycle, you have pumped the fluid. When you reach the boiler part, then your heat addition part has started at this point only. So can I say that this is nothing but constant pressure lines? So heat is added at constant pressure only in a boiler. And then your isentropic expansion in the turbine. So we can see isentropic expansion in the turbine. And then we have constant pressure heat rejection in the condenser. So can you see that we have same thing here also? Okay. So this is nothing but constant temperature also. Like here temperature is also constant. So can you see that this is the cycle which has mostly reached whom? This is the cycle which idealizes or idealization of whom? Of Carnot cycle. Yeah. So if somebody asks you that, tell me which is the cycle which is mostly or which mostly replicates Carnot cycle, then answer will be Rankine cycle. Okay. Now let us try to find out the modifications in Rankine cycle in order to, if I can find some change in heat input or change in efficiency even. So in order to find out change in efficiency, what is your thermal efficiency first? Thermal efficiency is 1 minus Q out upon Q in, right? So what you would do is that you will try to find out and you will try to alter the things in your Rankine cycle, and then you would see, you would compare this ratio, and then you will find out that your means efficiency has got changed or not. So there is one thing written that if you lowers the condensation pressure, so what happens here is that initially you are working with the cycle what? 1, 2, 3 and 4. And then you have started working with what? Then you have lowered the condenser pressure. So can you see this was the initial cycle, and then if I have lowered the condenser pressure, then what happens? Can I write down this cycle is 1 dash, 2 dash, 3 and 4 dash. So you can automatically find out what are the changes we can see when I compared 1, 2, 3, 4 and 1, 2 dash, 3 dash, 1, 2 dash, 3 and 4 dash. So tell me what is the net work here? Or sirf turbine work, only turbine work. What is the turbine work here in 1, 2, 3, 4, and what is the turbine work? So can I see here that I have more expansion, like I have expansion from T3 to T4. So can I see that my turbine work has got increased? Can you see one thing? Tell me. Yes, I can see the turbine work has increased. One, this is one modification which I can find. And then what is the heat input? Q supplied. So Q supplied in, like here, if this is QS, then if this QS is compared to this one, this turbine work is higher. Compared to this one, see, initially you have heat supplied from 2 to 3 in this case, but here you have 2 dash 2 3. So your heat supplied has also got increased. Right? So heat input requirements has also increased, but the temperature, the turbine work has also increased. So, but can you see that this increase is very few? Can you analyze that this increase part, like this part is very few. So this magnitude is less and this magnitude is higher. Then again my thermal efficiency is nothing but Qt W net upon what is Q supplied. So what will be the effect upon efficiency? Your efficiency will be higher. Yes or no? Why? Because your W net has also increased, your W turbine has increased, and simultaneously your heat supplies also got increased. And you must be wondering that why we are not calculating, this work like T1 to 2 and 1 dash to 2 dash. This is pump work, right? W pump, right? But this magnitude is very less compared to turbine work. So that is why I'm not worried about this part. I was only worried about turbine work and heat supplied. I was not worried about this part. Why? Because this part was not significant one. So that is why whenever I will be comparing efficiency, I will directly look after net upon the heat supply. So I can say that yes, my thermal efficiency has got increased. So this is the one. Okay, clear? And what about Q rejected? Q rejected, can you see that Q rejected here has got increased? Can you see? Your Q rejected was initially Q4 to Q1. In this case, it was Q4 to Q1 in the previous one, but here it is Q4 dash to 1. So this magnitude is higher, right? So Q rejected is also increased. Okay. So this is the effect of lowering the condenser pressure. So see, the turbine efficiency is changed by two. See, the turbine is not the right term. I can say that the cycles efficiency is changed by two things. If you can lower the T average is the what? Lowers T average is what? Lower low T average. Low T average is what? That here you are rejecting temperature, right? And here you are also rejecting heat. So the average temperature at which heat is rejected, here also the average temperature at which heat is rejected. If you are able to decrease this, what? This, if you are able to decrease or lower the which temperature, T low, right? Then you can see, your efficiency will got increased, and we have seen that our efficiency got increased. So this is one. Okay, let us now move to another modification. Okay, let us wait. Okay, let me say, I don't know why, what happened. So just a second, please. Okay, then when you are superheating the steam, then when you are superheating the steam, you are increasing what? T higher average. So when your T higher average is increased, then your efficiency will get what? Increased. And moreover, there is one more thing, is that if you are at this point, like you are at this point, and then you have increased till what? This point, then can you see the difference? Can you see the difference that your X value has also got increased? So the more important purpose, the main purpose of increase in superheat, main purpose of increase in superheat is main purpose of increase in superheat is what? That you can increase your dryness fraction. And what next is that, can you compare the efficiencies? Can you compare the efficiencies? Yes, we can. See. Oh, I could not see what did you write, please. You're trying to ask something. Hmm? Can you write that again if you wish to? As expansion process increase, efficiency will increase. Yeah, like efficiency is increasing. Why? Because yeah, but there is one thing always, that you will have to look after the heat supplied also. You will simultaneously will have to look after the heat supply also. But since your T higher average increases, your neta will increase. You will have to look after just one thing, that what is happening with the T average. If this T average increases, higher T average increases, efficiency increases, efficiency increases. And efficiency can increase with what? T average lower if this decreases. Okay, this is the one. Next, see, you can now, if you can find out what are the changes you can see. So now next is, if I increase in boiler pressure. So can you see that if I am increasing the boiler pressure, then what happens is that I was initially in this region, and then if I have increased the boiler pressure, then I have changed into this one. Then here what happens is that you can clearly see that there is some decrease in W net. This is the area initially we had, but now we don't have that area, right? So your W net is in decrease, but again, since you are increasing the pressure, that means you are increasing the saturation temperature as well. T saturation temperature has also increased. That means again, mean temperature of heat addition, mean temperature of heat addition has also increased. Addition has also got increased. And if this heat addition has also got increased, then can you see that your efficiency will also get what? Increased. Okay. So this is how you should be able to apply. You should be able to apply your what? Like you just draw the cycle, you draw the change, and then you will be automatically able to analyze or see what are the changes, right? So you did not to remember it, but just try to draw what is the changes they are willing for us to what, take into picture, and then you work upon that. Okay. Okay, let us now quickly move to a few more things. So there is one ideal reheat Rankine cycle. So again, what happens here in the reheat Rankine cycle, what you are trying to do is that, can you see, you are trying to, when you are trying to reheat, this is the part where you are reheating, and then you are expanding it. So first you are having expanding it at the higher pressure, so that is why it is called higher pressure turbine. And then you are heating it into the low pressure turbine, so that is why it is called low pressure turbine, and then you are reheating it. So this reheat is again done at what? Constant pressure. So here your pressure is constant. We need to remember these things, that pressure is constant, and then we are reheating it. Okay, got the idea? So what happens in the reheat? What do you think about the efficiency? So it depends upon the magnitudes. Again, it depends upon the magnitudes. Like what is your this temperature? Like here you have your W net increased, right? But your simultaneously your heat supplied has also got increased. So depending upon the situations you are working about, then you will have to, depending upon that, what is the working scenario. But in general, like let us say that if a question appears in the exam, then you can go with what, that your efficiency increases with the basic of what, that mean temperature of heat addition is increased here. Mean temperature of heat addition is increased. So heat addition of mean temperature is increased, then you can say that okay, the efficiency will somewhat get increased. Next is regenerative Rankine cycle. Likewise, we have seen in the turbines case, we have seen regeneration, right? So here also we have regeneration. So what we would do is that in this regeneration is that we will start from boiler, and then we have into the turbine. Then what we would do is that we will allow we will allow few part of the mass to fully get expanded, and then what I would do is that I will take some of the mass from this one, like expanded mass. Please take care that what I am telling you is that expanded mass, you will take some of the expanded mass here, and you will take it into whom? There is an feed water heater here. This is the example of open feed water heater. You will take it into heat, right? And then the condensed part comes here, and then what you would do is that you will install a pump. And then you will pour it into what? The open feed water heater. So can you see that here the open feed water heaters are meeting? See, I'm explaining you again. See, what happens here is that the uh, till some pressure, your whole of the substance has got expanded. But after that, what I have done, that a fraction of mass is taken out and is collected somewhere. Okay, so some of the mass has taken out and collected somewhere, and the rest of mass is expanded, and then its heat is rejected. And then what I have done now is that I have increased its pressure to whom? Increase its pressure to whom? To the which pressure? The pressure at which the initial extracted mass is kept, and then I will mix these two in a chamber. This chamber is called open feed water heater. Why? Because can you see is that your extracted, and the steams means what? This is condensed. This is condensed steam, and this is extracted steam. Both are meeting in a feed water heater which is open, means both are allowed to mix together. So that is why this is named as open feed water heater. And then the process continued like the previous one. You can add the heat, you can increase the pressure with the help of pump, and then you can add heat in the boiler, and then you can start working with the turbine. So this is the ideal regenerative Rankine cycle. Okay, so what is the benefit of it? The benefit of it is simply that, can you see one thing is that your your heat supply requirements has got decreased. Yes or no? Yes, because initially if there was no feed water heater, then you must have supplied heat from this point till what? From this point till this point. This is nothing but the part of boiler only. Okay, so till this point you could have supplied heat, but what happens with the help of feed water heater, your heat supplied part has rejected to very few. Yes or no? Yes. So your heat supplied part has been rejected to few. Okay. So this will again this will again increase what? Efficiency. This will again increase what? Efficiency. And what is the another benefit of doing this? The another benefit of doing this is that, see, there are some gases trapped while you are working with this turbine. Okay. So your open feed water heater here, both are allowed to mix in an open chamber. So what happens is that any dissolved gases which are there, so they can escape out. So dissolved gases can escape outside. Okay, so dissolved gases can go outside from this one. Okay, and then there is one example of, this is example of closed feed water heater. So what happens here is that the process is initially same, but what happens is that, can you see one thing, that again you have extracted some heat, but you have not allowed it to mix with whom? The condensed one. The condensed one which are coming is into what? Into the pipe, and the is into what? Closed feed water heater. So what happens here is that this gas, here we have gas form, right? So this is condensed with whom? That this is giving its heat to whom? To the condensed one, and it also gets what? Condensed. And then these two are collected at this pump two. Got the idea? Like this condensed part, like here what comes has not mixed into what? The coming from here. So what it has happened here is that it has got condensed by giving away its heat to what? The fluid in pipe, this pipe, and then it has got collected here. Then again this is supplied to a mixing chamber, and then this too has got mixed, and then it has supplied to the boiler, and then the cycle continues. Okay, so only difference is that here you have no mixing, and here earlier we had the mixing. Okay, so this is the application parts of thermodynamics. So mostly things will be focused upon these areas. So what happens to you is that you will have to what? Go and solve the questions from these areas, stick to the basics, and then what will happen that you will be able to solve most of the questions. Only thing you need to do is that whenever they are asking about comparison, you draw the cycle, you draw the new one as per they are trying you to do, and then you compare them. And similarly, for case of, let us say you are working with Brayton cycle, regeneration cycles, let us say you are working with Otto diesel, then whatever they are question trying to ask you is mostly based upon the cycle. So you try to remember those cycles, like how, what are the various process involved, how their TS and PB diagrams looks like, then most of the question will fall into those range, and then you will be able to solve them. Okay, so we'll stop here, and yeah, so practice the ample amount of questions so that you can do well in your examinations. Okay.